This one is another very important repeatedly asked question for the board from ray optics, the lens maker's formula. There are two basic assumptions in this derivation. We're assuming the object to be point size and is placed on the principal axis. And second one, the lens what we are imagining is assumed to be very thin. Means if the distance is measured from left surface or right surface of the lens, that is treated as equal. Even that is same as if it's measured from the center of the lens. So the lens is assumed to be very thin. And we already derived a formula for any refraction for spherical surface. N1 by minus u plus N2 by v equal to N2 minus N1 by r. Where r is the radius of curvature of the spherical surface. N1 is the refractive index of first medium. N2 is the refractive index of second medium separated by the spherical surface. U is the object distance and V is the image distance. Now the basic thing for the derivation for lens maker's formula using these facts is the ray diagram. Convex lens. Refractive index of the material of the lens is N2, medium surrounding is N1. So medium has a refractive index N1. Surrounding medium, other side also N1. The lens is made up of N2. It's the principal axis. We assume a point object O. Just for discussion, the top end is X, lower end is Y, and the left surface where the principal axis meets that point is P1, and the right side pole is P2. Now one light ray will go straight through the optic center. No deviation C. Another light ray falling on any one point of the first refracting surface XP1Y. If the second surface XP2Y were absent, imagining XP2Y were absent so that the right side is complete glass, no cutting like this, the light ray undergo diffraction from XP1Y and move after bending. It may meet at the principal axis, this light ray forming the image. So let this image be I1. But this is not the real case because actually there is a separation of media after XP1Y. XP2Y again makes separation between N2 and N1. That means two different media. One more refraction should take place at XP2Y. So this light ray cannot go straight. This is only the expected path of the light ray. The second refraction at this point will make the light ray bend further. So that will be the final image formed. So that's the actual image point I, the result of the second refraction. The first light ray bend towards a normal. Second light ray bend away from the normal. The final image is formed at I. So to get that bending towards a normal and away from the normal, like if this is the first surface, like this is the first surface. So this will be the center. So this will be the normal. So instead of light ray going out like this, it bent towards the normal, like this. This light ray is supposed to go straight. It's a normal for a sphere. Always line drawn from the center will be the normal. So instead of going straight, if it's going up, it will be away from the normal. It's bending towards a normal from rarer to denser, N1 to N2. Now, this light ray undergoing refraction from second surface. This will be the second surface. The center will be here. So if you draw the normal, this will be the normal. So this light ray, if it bend up, will be towards the normal. It's going from denser to rarer, so it bent away from the normal. That's why it's towards the principal axis. So you know the reason why the light ray is bending down, or at least the top end of the half of the lens can be taken as a prism, like this, similar to this. In a prism, you already learned the light ray bend towards the base. If the material is denser than the surrounding medium, bending towards the base. That is just for understanding why the light ray bend towards the normal. Now, the distance from O to P1, that is the object distance, U, and the distance from P1 to the first image, imaginary, which was supposed to be formed if the second surface were absent. It could not, because really the second surface is present. So that distance is V1. And the final image distance, because of the second surface forming the image, P2 to I, that's V. So these are the object distance, image distance for both the surfaces. So the ray diagram is complete. Now the derivation based on the diagram. We need to apply this refraction at spherical surface formula for refraction at the first surface xp1y, then second refraction at xp2y. To find the total refraction, we have to add the two refraction cases. So considering refraction from N1 to N2, the light ray entering lens from surrounding medium, maybe air or any other medium. These are the factors before the derivation part. N1 is the refractive index of the medium in which lens is placed. N2 is the refractive index of the lens. R1 is the radius of curvature of the first surface of the lens curved to the right. R2 will be the radius of curvature for the second surface of the lens. Now, like we discussed in the beginning, if the second surface xp2y were absent, the first surface forms image at I1. That means object distance is P1 to O, which is U. Image distance is P1 to I1, which is V1. So we can apply the values in the formula. N1 is N1 itself, first medium. Refraction is from N1 to N2, so first medium is N1. N2 is again N2. Object distance is U. The minus is already there in the formula. Image distance is V1 for the first surface. Radius of curvature will be R1. So if you apply the formula, the result will come as N1 by minus U plus N2 by V becomes V1, N2 minus N1 by R1. Now the image formed by the first surface xp1y will act as the virtual object for the second surface xp2y, or the image light ray from the first surface. This is the object light ray. The image light ray from the first surface will act as the object light ray for second surface, and the final image is formed at I. So for the second surface, the object distance will be the image distance of the first surface, and second surface, the image distance will be from P2 to I, which is V. So considering refraction from N2 to N1, the image formed by the first surface acts as a virtual object for the second surface, and the final image is formed at I by the second surface. So again, we can apply same formula with different result. Here N1 will be N2 because first surface is N2. N2 will be N1 minus the object distance will be the image distance for the first surface, which is V1. Then the final image distance will be V only. N2 minus N1 becomes second minus first will be N1 minus N2 by R becomes R2. So this is N2 minus N1. If you can take a minus out here, you get N2 minus N1. So just taking the minus out, N2 by minus V1 plus N1 by V equal to minus of N2 minus N1 by R2. N2 because the first medium is N2. N1 as second part because second medium is N1. The same way N2 minus N1 become N1 minus N2. The minus is already there. The object distance for the second case is the image distance of the first one. The image distance is the real image distance, what's V. Now we add 1 and 2 to find the total refraction. So when you add N2 by V1 and minus N2 by V1 get cancelled. N1 by minus U, that's left here, plus N1 by V, that's also left here. The other two terms get cancelled. Right hand side, N2 minus N1 by R1 plus minus of N2 minus N1 by R2. So N2 minus N1 can be taken common out. Here N1 can be taken common out. So N1 common out, 1 by minus U plus 1 by V equal to N2 minus N1 common out, 1 by R1 minus 1 by R2. Now you can divide throughout by N1. So dividing throughout by N1, this N1 get cancelled. Here N1 will come. No other difference. Just N1 transfer to the right side, N2 minus N1 by N1. This can be divided separately. So N2 by N1 minus 1. If you keep the object at infinity, the image is formed at the principal focus. So if U is infinity, V will be F. For an object at infinity, the image will be formed at the focus, means U is infinity, V is F. You can substitute here 1 by infinity and 1 by F. The rest part remains same. Like what you have done, you can change N2 minus N1 by N1 as N2 by N1 minus 1. So 1 by infinity will be 0. Will be 1 by F equal to N2 minus N1 by N1 into 1 by R1 minus 1 by R2. So this is basically Lensmaker's formula. So this one you can divide and keep it separate, N2 by N1 minus 1. And this will be same as the power. 1 by F is same as the power. So when you learn for numerical questions, it's good to learn n of the lens as N2 by n of the medium surrounding as N1 minus 1, which is same as the power or 1 by F into 1 by R1 minus 1 by R2. For numerical questions, R1, R2 should be given sign convention. For a convex lens, R1 will be positive, R2 will be negative. It's curved right for the first surface and curved left for the second surface. For a concave lens, first surface is curved left and second is curved right. So R1 will be negative and R2 will be positive. Now the focal length and power will be taken as positive for a converging lens and negative for a diverging lens. So these are the concepts behind the derivation, and when you apply the numerical questions, the formula, you need to apply the sign conventions. Object distance, I think it's not marked in this view. P1O is U. P1I1 is V1. Now P2I, that is V. But P1, P2 and C all are taken as identical points. Measured from P1 to I1 is same as C to I1, which is same as P2 to I1. P1, P2, C, all 3 points are taken as a single point.